Flow through orifice and mouthpiece can be studied using an experimental setup in our laboratory that can be described somewhat like this. So this is a simplified version of the main components of this experimental setup. So it consists of this kind of a reservoir which stores water, and from this reservoir a pump draws water and carries it to another tank which is at a higher level. So it supplies water to this tank, and in this tank there is an orifice, or if required we can replace that orifice with a mouthpiece. As you can see, the mouthpiece has a small tube attached to this plate, and in case of an orifice it doesn't have that tube, it is only simply the plate. So this plate, or the orifice plate, is attached to this opening, and through this water will come out. When water is supplied to this tank, in this tank there is a glass tube like this which is connected to this tank, and it will indicate the water level inside the tank, because we cannot take water level measurements inside the tank, so therefore we are going to take those measurements outside. So a scale is also attached here. Based on this we can find out what is the height of water inside the tank, and as water flows out of this orifice it will flow in this channel. A small channel is attached here, and through this channel water will flow through this opening at the end, and it will flow again back to this reservoir. So the circuit is complete. Whatever amount of water is drawn by the pump is again dumped back into this reservoir. Now this is a measuring tank. So while you are not performing the experiment, water will simply flow into this reservoir, but while we are trying to take any kind of discharge measurement, what we can do is this part of the outlet is actually movable. So using this handle we can rotate this whole thing like this, and water from this end will, instead of going directly into the reservoir, it will flow into this measuring tank. This measuring tank also has this kind of a water level indicator. So this water level indicator will show us the water level inside this tank. So what we will do is, for measurement of discharge, we will divert the water into this tank, and we will first note down the initial water level, whatever water was originally here. So based on that initial water level, we'll collect the water for a given amount of time, suppose 10 seconds or 20 seconds, which will be decided by us, and we'll collect water for that much time, and again we will rotate this back to its original position. So now we have collected this water for a known amount of time, and then again we'll note down the new water level here, and the new water level minus the old water level, original water level, will give us the change in water level, that multiplied by the cross-sectional area of this tank, which will be given to us, will give us the volume collected. So that volume collected divided by the time, whatever we decided, will give us the discharge, and that will be the actual discharge. Now the objective of this experiment is to find out coefficient of discharge, coefficient of velocity, and coefficient of contraction. So in case of an orifice, the coefficient of discharge is actual discharge by theoretical discharge. We have already discussed how to find out the actual discharge. Theoretical discharge we have to calculate. Now, actual discharge is actual velocity by actual area. and theoretical discharge is theoretical velocity by multiplied by theoretical area. Now in the numerator we still don't know what is the actual velocity and what is the actual area, but we know their product, although not individually these two terms, but their product is known to us because we can find out the actual discharge. For theoretical velocity and theoretical area, things is a little bit different, because as water comes out of this orifice, it gets contracted, and because it gets contracted, at some point all the streamlines become parallel, and that section is, that imaginary section in the jet of water, in the stream of water, is called the vena contracta. So that is considered the actual area of the jet or stream coming out of the orifice. Theoretical area is the area of the opening or area of the orifice, but actual area of flow is measured at that vena contracta. So you can write it like this: V actual multiplied by actual area, and the theoretical velocity, as we know, is given by root over 2gh, where h is the head of water above the orifice, and pi d square by 4 is the theoretical area, which is area of the orifice. So actual discharge is to be measured. Actual velocity also we have to measure. Diameter will be given to us, or we can measure it, and head we have to measure. Now how to measure theoretical discharge? For that, the formula is this much. There is theoretical area, that is pi d square by 4, whatever is the area of the opening, multiplied by the theoretical velocity root over 2gh. And this h measurement is actually very simple. We will collect water in the tank from which the orifice will discharge, but one main problem here is that this tank will take some time, because this pipe will supply it water at a certain rate, and at some other rate water will come out of this, so the flow will not remain steady. At some point this inflow rate is higher than the outflow rate, and sometimes this outflow rate may be higher than the inflow rate. So we have to wait for maybe a minute or two so that this inflow rate becomes equal to the outflow rate, and we can perform our experiment under a constant head. So that means when the inflow and outflow becomes equal, at that point the water level or the storage inside this tank becomes constant. So we'll have to wait for a minute to achieve that situation, that condition. So we'll have to wait for a while, and then we'll measure the water level from the level of the center of the orifice. So this scale may not be fitted exactly at the level of this orifice, so we'll have to find out what is the actual water level if we measure it from level of the center of the orifice. So from this level we'll have to first measure what is the reading of this scale at this level. So for example, this is the level of the orifice, and from this we'll measure what is the water level, suppose somewhere around here. So this reading minus this reading will give us the actual head. So then after getting head, we can find out the theoretical discharge using this formula. Theoretical discharge equal to pi d square by 4 multiplied by root over 2gh. Then actual discharge we've already discussed in the beginning. So we need to collect water in a measuring container or tank and measure the water volume collected during a given interval of time, and calculate the discharge as Q actual equal to volume collected divided by time. So this is the procedure. We'll collect the water for a pre-decided interval, suppose 15 seconds, 10 seconds, and before collecting whatever was the water level in that measuring tank, we'll note it down as R1, and after we have collected the water for 10 or 15 seconds, the new reading will be R2, and the volume collected will be that rise in water level multiplied by the cross-sectional area of the tank. So the actual discharge will be volume divided by time, that is R2 minus R1 multiplied by the cross-sectional area A divided by the time T. Now, the trickiest part in this experiment is the measurement of actual velocity. The theoretical velocity we already know, which is root over 2gh. Actual velocity may be calculated as actual discharge by actual area. But the problem is we do not know the actual area here, because that actual area is at the vena contracta. We know the area of the orifice, that is this bigger area is known to us, we can calculate. But this area we don't have any ways to measure this, because it will be a flowing stream. If you try to measure its diameter, the freely flowing jet or stream will be disturbed and we cannot take an accurate measurement. So we'll have to find it out by indirect calculations. So we'll do that based on the projectile profile of the jet of water. So the jet of water will flow like this. This red opening is the orifice, and from this blue stream of water is flowing out. Now this will follow the projectile path of the water particle flowing out at a velocity, at horizontal velocity. That means we can apply the kinematics equations for this kind of a stream. So in this stream, if this is the velocity at the outlet, and this velocity we are actually trying to find out, because till now we have not found out the actual velocity. So this will be the actual velocity. Then if you take any given time, any small interval of time, suppose t, then the horizontal distance traveled by this stream or any particle of water inside this stream is x, and the vertical distance traveled in the same amount of time is y, suppose. So this x will be given by x equal to velocity into time, and y will be given by 0 into t plus half gt square. This formula is just the familiar formula of kinematics, which is s equal to ut plus half at square, where s is the distance traveled, u is the original velocity, and a is the acceleration. In this case, in the vertical direction, the original velocity or initial velocity was 0, and the distance traveled, s is actually y, and the acceleration is, instead of a, we can write acceleration due to gravity, that is g. So finally we get y equal to half gt square. Or we can interchange the positions to get t equal to root over 2y by g, and then we'll put that value in this formula, and we'll find that x equal to this much, and finally we can write actual velocity v equal to x divided by root over 2yg by g. So this is how we can find out the actual velocity. But again, the main problem is to find out this x and y. So we have to take the measurement in the flowing jet of water. So for that we have a sliding point gauge fitted near the orifice. So this point gauge will be used for measurement of X and Y. So as you can see, there is a horizontal scale. Along with that, a vertical scale is also fitted. So this vertical scale can be slided. We can slide it along this horizontal scale. So what we'll do is, at the beginning, when water is flowing out of this orifice, we'll take this whole assembly, we'll slide it along this horizontal scale and bring it close to this orifice so that we can measure it approximately at the vena contracta. It's difficult to find the exact location of the vena contracta, but we'll take a very close section near to this outlet. So we'll slide this assembly like this, and then we will lower this needle down.
This apparatus is orifice and mouthpiece apparatus. In this apparatus, this is the sound tank and this is the measuring tank. Its area is approximately 0.1 meter square, and this is the constant overhead tank. This is the panel box. In this panel box, this is the main switch, and this is the indicator, and this is the pump. And this scale arrangement is to measure the flow rate of water through the measuring tank. And this is the drain valve for the measuring tank, and this is the drain valve for the sound tank, and this is the hopper arrangement. In this apparatus, we will determine the coefficient of discharge and coefficient of velocity. Then, for find out the coefficient of discharge, its formula is the actual discharge divided by the theoretical discharge. For actual discharge, first we have supplied 3 orifices and 2 mouthpieces through this apparatus. We have already given in the manual. Its diameter is, one diameter is 10 mm, another is 12 mm, and this is 15 mm. And this is the straight mouthpiece. That is, its L by D ratio is 2.5, and its diameter is 10 mm. And another is a converged mouthpiece. All for these orifices and mouthpieces, we will determine the coefficient of discharge and coefficient of velocity. To determine the coefficient of discharge, first we will put, suppose I want to test for the 10 mm orifice, then I will fix this orifice by opening these fly nuts. Then I will put the orifice to have to test, then to be tested, then I will tight this fly nut. Then after, I will switch on the pump. This is the constant overhead tank arrangement. For to maintain the constant level, there is a valve at the lower side of the tank. By opening or closing the valve, first I will fix the level of water at a particular level. Suppose I will fix 48 or 47 or 46. For determining the coefficient of discharge, its formula is actual discharge divided by the theoretical discharge. For actual discharge, measure the amount of water for a particular time, rise of water for a particular time in the measuring tank. Then this will give this formula is Q is equal to A into R divided by time. A is the area of the tank, R is rise of water, and T is time for rise of that particular amount of water. Then this will give the actual discharge of water. For calculating the theoretical discharge of water, for determining the theoretical discharge, its formula is A0 into root over 2H. H is the head of the water in the constant overhead tank, and A0 is equal to 5 by 4 into D square. D is the diameter of the orifice or mouthpiece. Then by putting the formula actual discharge divided by the theoretical discharge, I will calculate the coefficient of a discharge. First, for conducting the experiment, first I will maintain the level of water at a particular level by opening or closing this valve. Suppose the water level is rising, then you just open this control valve. Suppose the level is now its level is 46.5. Its level is approximately 46.5. Now that means its head is, that is the capital H is 46.5. At 46.5, for calculating the theoretical discharge, that is the head of water root over A0 into root over 2ds. This is the value of H, and this value of the diameter, its diameter is 10 mm. That means pi by 4 into d square. Its value will give the A0. By putting the formula A0 into root over 2gs, its value will give you the theoretical discharge. Then for calculating the actual discharge, close this valve and collect some amount of water for a particular time. Suppose I will collect water for 2 minutes. Suppose now initial level is 0. Suppose after 1 minute, now its level is 9.5 centimeter. Initial level was 0 and the final level is 9.5. Then the final level minus the initial level give the value of rise in water, and the time is 1 minute, that is the 60 seconds. A is the area of the tank, that is 0.1 meter square. Put all the values in the formula and determine the actual discharge. This and actual discharge divided by the theoretical discharge, its value will give the coefficient of discharge. For calculating the CV, its formula is x divided by root over of 4 into y into h. For calculating the x and y, toss this pointer to the lower surface of the water. Lower surface of the water. Now its value is 21.5, 21.3. Its initial value is 21.3, and the final value is 28.5. Final minus initial, this value will give the x, that is the vertical height. That means its value will give the y. And for calculating the x, slide this pointer to the last point of the water, and this value, this initial value was 4.5 centimeters, and the final value is that is 37. That is 37. Now final minus initial, this value will give the x, and for y, final minus initial, the value will give the y. Now put it in the formula, that is x divided by 4 into y into h, and determine the coefficient of velocity, that is the CV value.